See this question. The resistances of wire at a temperature T degrees and 0 degrees are related by. So we know the temperature dependence of resistance. So R is equal to R naught into 1 plus alpha into delta T. Right. So this is what is going to be the answer. So RT, obviously, it's going to be RT, which is going to be R naught into 1 plus alpha into delta T. So the answer is option A. See this question. Resistance of the wire is measured as 2 ohms and 3 ohms at 10 degrees Celsius and 30 degrees Celsius respectively. Temperature coefficient of resistance of the material of the wire is. So temperature coefficient of resistance, they are asking alpha. Right. So we know pretty well R is going to be equal to R naught into 1 plus alpha into delta T. Right. So they have given you two resistances. So resistance of the wire is measured as 2 ohms and 3 ohms, which means they are changing the temperature alone, they are not changing the material. Right. So for 2 ohms it is going to be 10 degrees Celsius and for 3 ohms it is going to be 30 degrees Celsius, and they are asking us to find temperature coefficient of resistance. So let us first consider the first case. So 2 is going to be equal to R naught into 1 plus alpha into 10 degrees, and 3 ohms is equal to R naught into 1 plus 30 alpha. So when you are taking the ratios, you can easily find out. So when you are taking the ratios, what you will get? R naught cancels. So you will be having 2 plus 60 alpha is equal to 3 plus 30 alpha. So 60 minus 30 becomes 30 alpha, and 3 minus 2 becomes 1. So alpha is going to be 1 by 30. So it is going to be 0.033 per degree Celsius. Right? So 1 by 30. So it's going to be 0.033 per degree Celsius. So see this question. At 1000 degrees Celsius, the resistance of a wire is found to be 4 times its resistance at 0 degrees Celsius. So which means RT is going to be 4 times R naught, say for example. So RT is going to be at 1000 degrees Celsius and R naught is going to be at 0 degrees Celsius, and they have told you that it is going to be 4 times. The temperature coefficient of resistance of the material of the wire will be. So you know pretty well temperature coefficient of resistance directly what we can deal with this. So 1 by R naught delta R by delta T, right. So in this case delta R is going to be RT minus R naught divided by R naught into change in temperature 1000 minus 0. So RT is going to be what? 4 times R naught minus R naught divided by R naught into 1000. So it's going to be 3 R naught by R naught into 1000. So it's going to be 3 into 10 power minus 3, which means 0.003. So 0.003 per degree Celsius. So the answer is option C. See this question. The temperature coefficient of wire for a wire is 0.00125 per degree Celsius. At 27 degrees Celsius, its resistance is 1 ohms. The temperature at which the resistance becomes 2 ohms is. So obviously we know what is going to be the formula. So we can take directly as alpha is equal to R T minus R divided by R naught into T2 minus T1. So they have given you alpha, they have given you what is T1, they are asking us to find what is T2, and RT is 2 ohms and R1 is going to be 1 ohm, right. So we can take directly T2 minus T1 is equal to RT minus R naught by R naught into alpha. So which is going to be RT is going to be 2 ohms minus 1 divided by R naught is equal to 1 into alpha is going to be 0.00125. And T1 is going to be 27, right. So T2 will become, so 1 by 0.00125 plus 27. So 0.00125 can be written like 0.008 into 10 power 5 in plus 27, which is going to be 8 into 10 square plus 27, which means 800 plus 27, 827 degrees Celsius. But the options are in Kelvin. So what do you have to do? So in order to change it, you will be adding it with plus 273. So it's going to be 1100 Kelvin. So the answer is option B. See this question. The voltage V versus current I graphs for a conductor at two different temperatures are shown in the figure. The relation between T1 and T2 is. So this is what is VI graph which we have. So whenever a graph is drawn with respect to V and I, obviously its slopes gives you resistances, right? So and also the slope can be written like tan theta, right? So tan theta is nothing but y by x, which is going to be V by I, which is going to be R. So the temperature which they're asking us to relate the temperature, right? So which temperature is going to be greater, T1 or T2? Obviously the angle of T1 is going to be greater, which means theta 1, theta 2. So theta 1 is going to be greater than theta 2. So T1 is going to be greater than T2. If it is going to be I versus V, it's going to be opposite, right? So the answer is option A, T1 greater than T2. See this question. We use alloys for making standard resistors because they have option A, low temperature coefficient of resistivity and high specific resistance, high temperature coefficient of resistivity and low specific resistance, low temperature coefficient of resistivity and low specific resistance, high temperature coefficient of resistivity and high specific resistance. See, basically we go for alloys, right? So alloys has a property of metals as well as non-metals. So basically, say for example, we take an heating element. So heating element, what it does, it should allow the current, at the same time it has to resist at a higher value so that it will produce some heat. That is what is Joule's law of heating. So when a high amount of current passes through high resistance over a period of time, it is going to heat up. So when the material heats up, it should not melt. So what are the conditions to be taken care? So when a material has to not melt much, it has to have low specific coefficient of resistance, right? So which means coefficient of temperature should be less, and it has to have high resistivity also. So the option should be low temperature coefficient of resistivity and high specific resistance. Then only it provides proper standard resistors for us. So it should not melt, at the same time it has to withstand the heat without melting, and it has to resist high. It has to conduct too, right? So this is how the geysers and water heater works. So alloys are used for heating elements for this purpose only. See this question. A lead acid battery of a car has an EMF of 12 volt. If the internal resistance of the battery is 0.5 ohms, then maximum current can be drawn from the battery will be. So basically the formula for maximum current whenever the internal resistance plays a role. So the maximum current has a formula of E by R, where E is EMF, R is going to be internal resistance. So what is E? So 12 volt and internal resistance is 0.5. So obviously it is going to be 24 amperes. So the answer is 24. See this question. A battery of EMF 10 volt and internal resistance 3 ohms is connected to a resistor as shown in the figure. If the current in the circuit is 0.5 amperes, what is the resistance of the resistor? So they are asking us to find what is going to be R, and they have given you the current also. So I is equal to 0.5 amperes. So whenever an EMF is, whenever a load actually draws some current from the EMF of a cell, then the formula will be with respect to the current also, you can take it like I is equal to E by R plus R, where R is internal resistance and capital R is going to be external resistance, and the question we here asked is capital R, right? So what we can do is we can rearrange this. So R plus R is equal to E by I, and R is going to be E by I minus R. So you know what is E? So E is going to be 10 volt and the current is going to be 0.5 and the internal resistance is going to be 3. So it's going to be 20 minus 3, which is going to be 17 ohms. So the answer is 17 ohms. See this question. A cell of EMF 1.5 volt and internal resistance 2 ohms is connected to two resistors of 5 ohms and 8 ohms in series. The potential difference across 5 ohm resistor will be. So whenever there is question without circuit, we have to first draw the circuit, so to understand what is happening. So there are two resistors which are in series, which is going to be 5 ohms and 8 ohms, and they are connected to an EMF of a cell which is going to be having an internal resistance of 2 ohms. So this is going to be 1.5 volt and this is going to be 2 ohms, and they are asking what is going to be the potential difference across 5 ohm resistor. So obviously we know pretty well, we have to first evaluate what is going to be R equivalent, and then we can directly find out current, and then we can substitute it with V is equal to IR. So I is going to be equal to E by R equivalent plus R. where E is going to be 1.5, R equivalent is 2 resistors connected in series. So directly we can add those 2 resistors because current is going to be same. So 5 plus 8 is 13 plus 2. So it's going to be 1.5 by 15, which is going to be how much? 1.5 by 15 is going to be 15 tens are. So 1 by 10. So it is going to be 0.1. So 0.1 amperes, and V1 is equal to I R1. So which is going to be 0.1 into R1 is going to be 5. So it's going to be 0.5 volt. So the answer is 0.5 volt. You have an alternate method for this also. So we have something called as voltage division rule. What it states is the potential through an individual resistor can be found out by equating it with same resistance divided by total resistance into total potential. So R1 is going to be what? So it's going to be 5 divided by 5 plus 8 plus 2 into 1.5. So how much it is going to be? 5 by 15. So 5 by 15 into 1.5. So it's going to be 0.1. So it's going to be 0.5 volt. So without calculating current, you can go directly with this also. So this is nothing but potential division rule or voltage division rule. See this question. When a current of 0.2 amperes is drawn from a battery, the potential difference between its terminals is 20 volt. So let it be I1, which is going to be 0.2 amperes. So the potential difference between the terminals is going to be 20 volt. When a current of 2 amperes, which means I is equal to 2 amperes, then the potential difference drops to 16 volt. So V2 is going to be 16 volt. So we have to be very careful in drops to and drops by. So drops to 16 means it is going to become 16 volt. Drops by 16 is, so it is going to reduce by 16 volt, which means if it is going to be already 20 volt, if it drops by 16 volt, then it's going to be 4 volt. So drops to 16 volt means it's going to be 16 volt. Oh, okay. So you have to be very careful in understanding the question. So V2 is going to be 16 volt. So they are asking us to find what is the EMF of the battery. So they didn't change the battery, so it's going to be remaining the same. So according to this, the battery is going to release some current, which means the load is going to draw some current, right? So we know according to the discharging case of cell that the potential that the terminal voltage will be V is equal to E minus IR. So V1 I1 and V2 E minus I2R. So what we will do is we will just substitute it. So V1 is going to be 20 minus is equal to E minus I1 is going to be 0.2 R. The other one is going to be 16, which is going to be E minus 2 times R, right? So you have to just equate it. I mean, you have to solve these two equations to find out what is the answer. So we require E, correct? So what we will do is we will just multiply the first equation with 10. So we will have 200 is equal to 10E minus 2R, and this will be 16, which is equal to E minus 2R. So minus plus, so it will cancel. So you will be having 184, which is going to be 9E, right? So what will be E now? E is going to be 184 by 9. So it is going to be 2 times 0, 9 4s are 36. So 20.4. So the answer is 20.4 volt. See this question. If 3 amperes of current is flowing between the points P and Q in the circuit, then the potential difference between P and Q is. So in the circuit, the 3 amperes flows here and there is an EMF of a cell and the internal resistance and a 4 ohm resistor. They are asking us to find what is going to be the potential difference across P and Q. So which means VPQ, which is equal to VP minus VQ, which is nothing but E plus I into R plus R, right? So what is E here? It's going to be 2 and plus I is going to be 3 and R is going to be 4 plus internal resistance 2. So it's going to be 6 into 3, 18 plus 2, 20 volt. So the answer is going to be 20 volt. See this question. For a cell, the terminal potential difference is 3.6 volt when the circuit is open. If the potential difference reduces to 3 volt when the cell is connected to the resistance of 5 ohms, the internal resistance of the cell is. So basically internal resistance is equal to E minus V by V into R. So see the question carefully. For a cell, the terminal potential difference is 3.6 volt. When the circuit is open, okay, so when the circuit is open means they are only measuring what is going to be the potential across the cell, which is called as EMF. That is what they have mentioned it. If the potential difference reduces to 3 volt when the cell is connected to a resistance of 5 ohms. So they are connecting the cell to a 5 ohm resistor and the potential drops to 3 volt. So now they are asking us to find what is internal resistance of the cell. So what we can do, E is going to be what? 3.6, because they have measured that the potential across the cell in open circuit. Open circuit means there is no load in it. So that is going to be EMF and minus the potential which it reduces to, and R is going to be 5. So it's going to be 0.6 by 3 into 5. 0.6 by 3 into 5, which is going to be 0.2 into 5, which is going to be 1 ohm. So the answer is 1 ohms. See this question. A straight line plot showing the terminal potential difference V of a cell as a function of current I drawn from it is shown in the figure. The internal resistance of the cell would be then. So they have potential versus current and they are asking us to find what is going to be the internal resistance of the cell. So let us see the markings here. So at 0 current, the voltage is going to be 5.6. So let me consider I1 as 0 amperes. So the potential will be equal to 5.6 volt. And likewise, if I2 is going to be 2, then V is going to be 0. Right. So according to this, we have to find out what is going to be the internal resistance. So what is the formula for internal resistance? It is nothing but E minus V by I. Right. So what is E here? So it's going to be the maximum potential, which is going to be 5.6 to 0 by the current is going to be 2. So it's going to be what? It's going to be 2.8 ohms. So the answer is 2.8 ohms. See this question. 6 identical cells, each of EMF 6 volt, are connected in parallel. The net EMF across the battery is. So it is nothing but grouping of cells. So whenever grouping of cells are being done, so if it is going to be series, the current remains same and the EMFs are going to vary and we have to add the total EMF of the cell. But in this case, it's going to be parallel, which means EMF is going to remain same, but the current is going to be different. So they have given you 6 identical cells of 6 volt connected in parallel, which means what? It's going to be in parallel, so the potential is not going to change. So each and every cells are going to have 6 volts. So the equivalent EMF is going to be 6 volt again. See this question. 2 similar accumulators, each of EMF E and internal resistance R, are connected as shown in the adjacent figures. Then the potential difference between X and Y is. So this is what is X and this is what is Y. So they are asking us to find what is going to be the potential differences. And you can see both the accumulators, which is nothing but cells, are being connected in opposite direction, which is going to oppose each other. So obviously there won't be any potential difference. So Vx minus Vy will become 0. So the answer is 0. See this question. If the resistance of the wire is made 4 times, keeping potential difference across it constant, then the number of times heat produced in it varies by. So they are relating heat, potential difference and the resistance, correct? So what is going to be the formula for energy or heat? So obviously we will be relating it as V square by R into T, correct? Because they are not going to vary time. So obviously this is what is going to be the case. And what happens here? If the resistance of the wire is made 4 times, so resistance of the wire is going to be 4 times, which means H dash is going to be inversely proportional to 4 times R, right? Keeping potential difference across it constant, so it is not going to vary. So then the number of times the heat produced will be. So we know pretty well now. So H dash by H can be equated as 1 by 4. So it's going to be 1 by 4. See this question. A hot electric iron has a resistance of 80 ohms and is used on 200 volt source. The electrical energy spent if it is used for 2 hours. So we know pretty well potential, resistance and voltage with respect to time. So obviously the energy can be written like V square by R into T, where V square is going to be 200 into 200 and time is going to, because the options are in hours only, so watt hours, so we can take it as it is, and R is going to be 80. So it's going to be 1000 watt hours. The answer is 1000. Okay, see this question. If the percentage change in current through a resistor is 1%, then the change in power through it would be. So we know P is going to be equal to I square R. They have asked you power only, right? So change in power means, so delta P by P into 100 can be written like 2 delta I by I plus delta R by R into 100. This you would have studied it in errors of your units and measurements in 11th standard, the similar case only, but we have taken that into care because this is what is the change in power denotes with percentages. So delta P by P into 100, so it's going to be 2 into delta I by I, so it is going to be what, 2 times 1%, so it's going to be 2%. So the answer is 2% because resistance is not taken care.